Areas and arc length using polar coordinates. The basic area problem. We want to compute the area of a region in which r is between 0 and f of theta, and theta is between angles alpha and beta. Here's a generic picture of such a region. Notice that it's bounded by the graph of r equals f of theta, and raised theta equals alpha and theta equals beta. To find its area, we need to know how to express the area of a typical polar slice, which has the shape of a wedge that's approximately a small circular sector. Suppose it's located at some theta between alpha and beta, and that it corresponds to a small change delta theta in the angular coordinate. The area delta A of this polar slice is approximately equal to the area within a circle of radius f of theta, which is pi times f of theta squared times the fraction delta theta over 2 pi. So we have delta A approximately equal to 1/2 of f of theta squared times delta theta. This leads us to the area differential dA equal to 1/2 f of theta squared d theta, or 1/2 r squared d theta. And the area of the region will be the integral of dA from theta equals alpha to theta equals beta, which is the integral from alpha to beta of 1/2 f of theta squared d theta. Example. Find the area inside the cardioid r equals 1 plus cosine theta. Here's the region whose area we want to find. The integrand in the integral for the area will be 1/2 of 1 plus cosine theta quantity squared. The region is swept out as theta goes from 0 to 2 pi. So we integrate from 0 to 2 pi. By symmetry, this will equal 1/2 of 2 times the integral from 0 to pi, so the area will equal the integral from 0 to pi of 1 plus cosine theta squared d theta. To compute this, let's first expand the integrand, which gives 1 plus 2 cosine theta plus cosine squared theta. Now let's rewrite cosine squared theta as 1/2 of 1 plus cosine 2 theta, and now simplification gives us the integral from 0 to pi of 3/2 plus 2 cosine theta plus 1/2 cosine 2 theta d theta. So now we antidifferentiate, getting 3/2 theta plus 2 sine theta plus 1/4 of sine 2 theta, which we evaluate from 0 to pi. The value of the antiderivative at theta equals pi is 3/2 times pi plus 0, and the value at 0 is 0, so the area is 3/2 pi. Example. Find the area inside one leaf of the 3-leaved rows r equals sine of 3 theta. Here's the region whose area we want to find. The integrand in the area integral will be 1/2 of sine squared 3 theta. The limits of integration correspond to the angles indicated here, the first of which is obviously theta equals 0. The upper limit of integration will be the first positive value of theta, where sine of 3 theta is equal to 0, which happens when 3 theta equals pi, that is, theta equals pi over 3. Thus the region is swept out as theta goes from 0 to pi over 3. So we integrate from 0 to pi over 3. Now let's rewrite sine squared 3 theta as 1/2 of 1 minus cosine 6 theta, and then antidifferentiate, obtaining 1/4 of theta minus 1/6 sine of 6 theta, which will evaluate between 0 and pi over 3. At pi over 3, sine of 6 theta equals sine of 2 pi, which is 0. So the value of the antiderivative at pi over 3 is 1/4 times pi over 3 minus 0. The value at 0 is 0, so we have pi over 12 as the area of the region. Area between polar curves. Our goal here is to compute the area of the region in which r is between g of theta and f of theta, where g of theta is greater than or equal to 0 and f of theta is greater than or equal to g of theta, and theta lies between two angles alpha and beta. Here's a generic picture of such a region. Notice that its inner boundary is the graph of r equals g of theta, and its outer boundary is the graph of r equals f of theta, and it lies between the rays theta equals alpha and theta equals beta. The area differential here is dA equals 1/2 of f of theta squared minus g of theta squared d theta. And the area of the region is 1/2 of the integral from alpha to beta of dA, or f of theta squared minus g of theta squared d theta. Notice that this integral equals 1/2 the integral of f of theta squared, which gives the area between the origin and the outer boundary, minus 1/2 of the integral of g of theta squared, which is the area between the origin and the inner boundary. Example: find the area of the region that is inside the circle r equals 2 cosine theta and outside the circle r equals 1. These are the two circles, and here's the region whose area we want to find. To find the limits of integration, we need to find the values of theta where the circles intersect. So we set 2 cosine theta equal to 1, which is the same as cosine of theta equals 1/2. The solutions we want are plus and minus pi over 3, since it's clear that the region is swept out once as theta goes from minus pi over 3 to pi over 3. So the area of the region equals the integral from minus pi over 3 to pi over 3 of the square of 2 cosine theta minus 1 squared d theta. By symmetry, the integral here equals 2 times the integral from 0 to pi over 3, so the area will equal the integral from 0 to pi over 3 of 4 times cosine squared theta minus 1 d theta. Now let's rewrite cosine squared theta as 1/2 of 1 plus cosine of 2 theta, and simplify. Now we antidifferentiate, obtaining theta plus sine of 2 theta evaluated from 0 to pi over 3. Now evaluating at pi over 3, we get pi over 3 plus the sine of 2/3 pi minus 0, which equals pi over 3 plus the square root of 3 over 2. Example: find the area of the region inside the first quadrant that is inside the rows r equals sine 3 theta and outside the circle r equals sine theta. Here's a picture of the rows in the circle. The region in the first quadrant that's inside the rows and outside the circle is shaded here. Note that the outer curve is the rows and the inner curve is the circle. So the integrand of the area integral will be 1/2 of sine squared 3 theta minus sine squared theta. The upper limit will be the least positive solution of the equation sine 3 theta equals sine theta. Since 3 theta will evidently be a second quadrant angle with the same sign as theta, 3 theta and theta will be supplementary angles. That is, 3 theta will equal pi minus theta, or 4 theta equals pi, which gives us theta equals pi over 4. So we'll integrate from theta equals 0 to theta equals pi over 4. To compute the integral, we'll first rewrite sine squared theta as 1/2 of 1 minus cosine 2 theta, and sine squared 3 theta as 1/2 of 1 minus cosine 6 theta. Now simplification gives us 1/4 the integral from 0 to pi over 4 of minus cosine 6 theta plus cosine 2 theta d theta. An antiderivative of minus cosine 6 theta is minus 1/6 sine of 6 theta, and an antiderivative of cosine 2 theta is 1/2 of sine of 2 theta. So after a bit of simplification, we have 1 over 24 times 3 sine 2 theta minus sine 6 theta, which we evaluate from 0 to pi over 4. This equals 1 over 24 times 3 sine of pi over 2 minus sine of 3 halves pi minus 0. Sine of pi over 2 is 1, and sine of 3 halves pi is minus 1, so this equals 1 over 24 times 3 plus 1, or 1/6. Length of a polar arc. Consider a polar arc, r equals f of theta, where theta is between alpha and beta. Recall that the general form of the arc length formula is ds equal to the square root of dx squared plus dy squared. If we divide by d theta squared under the radical and multiply by d theta outside the radical, this becomes the square root of dx d theta squared plus dy d theta squared all times d theta. Now let's compute the expression under the radical, the sum of the squares of dx d theta and dy d theta. Since x equals f of theta times cosine theta, the product rule says that dx d theta equals f prime of theta times cosine theta minus f of theta times sine theta. Since y equals f of theta times sine theta, the product rule says that dy d theta equals f prime of theta times sine theta plus f of theta cosine theta. Now when we expand these products, there will be an f of theta squared times sine squared theta term, as well as an f of theta squared times cosine squared theta term, the sum of which is just f of theta squared. There will also be an f prime of theta squared times sine squared theta term, as well as an f prime of theta squared cosine squared theta term, the sum of which is f prime of theta squared. The other two terms are plus and minus f of theta times f prime of theta times cosine theta sine theta, which sum up to 0. So all we have is f of theta squared plus f prime of theta squared. So ds is equal to the square root of f of theta squared plus f prime of theta squared times d theta, which we can also write as the square root of r squared plus dr d theta squared d theta. And the length of the arc is the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta, which we can also write as the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. Example. Find the perimeter of the cardioid r equals 1 plus cosine theta. Here's the cardioid. Recall that it is traced out as theta goes from 0 to 2 pi. Since the top half is traced out as theta goes from 0 to pi, we can take advantage of symmetry and compute the perimeter as 2 times the integral from 0 to pi of 1 plus cosine theta quantity squared plus the square of dr d theta, which is sine theta. Multiplying out 1 plus cosine theta squared gives 1 plus 2 cosine theta plus cosine squared theta. The cosine squared theta term there plus sine squared theta equals 1, so the integrand becomes the square root of 2 plus 2 cosine theta. And factoring off the square root of 2, we now have 2 root 2 times the integral from 0 to pi of the square root of 1 plus cosine theta d theta. Now to find an antiderivative of the square root of 1 plus cosine theta, let's multiply and divide by the square root of 1 minus cosine theta. The numerator there is the square root of 1 minus cosine squared theta, which, for theta between 0 and pi, equals sine theta. Now we can find an antiderivative by substituting u equals 1 minus cosine theta, for which du equals sine theta d theta. The limits of integration become 0 to 2, since u equals 1 minus 1 equals 0 when theta equals 0, and u equals 1 minus negative 1 when theta equals pi. An antiderivative of u to the minus 1/2 is 2 times u to the 1/2 power, so we have 2 root 2 times 2 root u evaluated between 0 and 2. So the perimeter of the cardioid is exactly 8. Now we need to make a subtle point here. The integral from 0 to 2 of 1 over the square root of u du is an improper integral, since the integrand has a vertical asymptote at the left endpoint of the interval. So strictly speaking, the integral from 0 to 2 needs to be understood as the limit as a approaches 0 from the right of the integral from a to 2. And the evaluation of the antiderivative at u equals 0 needs to be understood as the limit as a approaches 0 from the right. The final result is the same. One more example. Find the length of the curve r equals theta for theta between 0 and 2 pi. Here's the curve. Observe that r equals 0 when theta equals 0, r equals pi over 2 when theta equals pi over 2, r equals pi when theta equals pi, r equals 3 pi over 2 when theta equals 3 pi over 2, and r equals 2 pi when theta equals 2 pi. Since dr d theta equals 1, the length of the curve will be the integral from 0 to 2 pi of the square root of theta squared plus 1. To evaluate this integral, let's make a tangent substitution. Let theta equal tangent phi. Then d theta is equal to secant squared phi d phi. And the integrand becomes the square root of tangent squared phi plus 1, which is secant phi, times secant squared phi d phi. So we have the integral of secant cubed phi d phi. Phi is the inverse tangent of theta, so phi equals 0 when theta equals 0, and phi equals the inverse tangent of 2 pi when theta equals 2 pi. So the limits of integration become 0 to the inverse tangent of 2 pi. Now recall that secant cubed phi may be integrated by parts, and the result is 1/2 secant times tangent plus the natural log of the absolute value of secant plus tangent. Now we need to evaluate this between 0 and the inverse tangent of 2 pi. The tangent of the inverse tangent of 2 pi is of course 2 pi. Since secant squared equals 1 plus tangent squared, the secant of the inverse tangent of 2 pi is the square root of 1 plus 4 pi squared. Now the second term is the natural log of the sum of those same numbers. This is the exact value of the arc length, which turns out to be approximately 21.26.